Okay, so that is the p value that I got. Let me just adjust this first. Now what we will do, we will check for the axial compression about the minor principal axis. Okay, so the slenderness ratio again we will work out. Right, for that particular axis. So the same step we need to repeat again. Okay, so I'm not writing the equation again. Above we earlier we have calculated that is for the major axis. Now we will work out the same for the minor axis in order to work out the compression capacity, right? So I'm not writing the equation again, I'll directly put the value. Okay, 2.44 rz, r that is the radius of gyration, pi square into this. Now if I work out this, okay, so I'm getting the value as 1.139. okay, similarly we will work out the phi as well. Okay, so 0.5, what was the earlier equation? We have this 0.51 plus a lambda z minus 0.2 plus lambda z square. So the way we have worked out for the major axis, similarly I am putting the value for the minor axis as well. And I am getting, that's a slight mistake, I'll get the value as 1.379. alright, and similar manner we will work out after the working phi value, we will work out the psi value as well. So phi underscore phi square minus lambda square, right? This is, I'm putting it at -1 in the inverse proportion, right? Because it's actually 1 divided by this value, so I'm writing it over here something like this. So we get the value as 1.379 plus the value of phi square minus 1.139 that we have got it earlier, right? So I'll get the value as 0.464. okay, and now for that particular the FCD value, that is for the minor axis, will be xi into Fy divided by gamma m0. So 0.464 into 250, that is your yield strength, divided by gamma m0 1.1, that is the factor. Okay, and here 0.464 into 250 into 10 raised to 6, I'm getting the value as 105.4 megapascal. Okay, so I'll work out the FCD as well. So my PD value will be, see, it's the same that we usually do during our graduation, right? No more difference. Here I am just explaining you with respect to the STAAD calculation, so it's that easy. You can do it by yourself as well, just you need your clear understanding. I have put it the area value for that particular portion, right? AE we already know that you can get from your steel table part for our angle profile. Okay, and 105.4 megapascal. Okay, so ultimately I am getting the value as 421.8 megapascal. So you have worked out this particular and now we will check for axial compression against the flexural torsional buckling. So see, since the member being designed is an angle loaded through one leg. Okay, that's the assumption that we have made. The axial compression capacity with respect to the flexural torsional buckling must be checked, that you need to work out. Okay, and the end conditions or the end connections, we are assuming that minimum 2 bolts is required, right? So that's the another portion, right? Because see, when you work out your lambda value, where you need to put your k1, k2, k3 value, for that part you will require this particular values from your clause 7.5.1.2. you can check out in the code from where and that's a clear understanding, where you have to take your k1, k2 and k3 value. Okay, so we are assuming first thing, the angle loaded through one leg. Okay, and we will check that particular for the flexural torsional buckling, as it is loaded through one leg. And the end connection, we are assuming what you can say, the minimum 2 bolts, or it's welded. Okay, so the end condition that we have assumed is what you can say is unrestrained, or you can call it as hinge, and therefore we have taken k as 1. Okay, so don't get confused with that. Now let me take the another paper. Now in order to work out the lambda value, okay, so from clause what you can say 7.5.1.2 lambda e, I'll make it k1 plus k2 lambda whole square plus k3 into lambda square. Okay, I am assuming that you all are aware with the Codal equation part, the basic calculation that we usually do in the graduation. So here I am not going into much detail, because I need to validate these values with your what you can say the STAAD example as well. So it will be a long video, right? So I'll try to minimize the efforts, but I'll try to cover the fundamentals. Okay, so you just need to go through these steps. You can find this particular steps in any good steel design book, right, that you are referring. So ultimately you can find these steps in your books as well. Okay, but here as we are validating these results with the STAAD calculation, it's necessary to cover all these steps. Okay, so we are doing that. So now let's work out the lambda value. So b plus d divided by 2t divided by pi square into e divided by 250 epsilon. Okay, so that's the equation. I'll work out the values for our angle profile. Okay, you have b and d, that is from your angle profile. What is our angle profile? We have considered the angle profile as you know, right, angle section ISA 150, 115, 16, right? So for this section we have worked out the b and d value, and based on that I am working out again the lambda part. Okay, so 150 plus 115 from here, divide by 2t. T is the thickness. Okay, so this divide by 2 into 16. Now again we need to work out the epsilon as 1, as we have already worked out. Pi square into e value, we are already aware with this, divide by 250, right? So let's just calculate this, and we will get the value as 0.092. Okay, so from that we will simply get the lambda VV as well. This is your radius of gyration, epsilon pi square e divide by 250, 250 divide by 2.44. Ultimately I am getting value as pi square, again 205 into 10 raised to 3 divided by 250. So I'm getting this particular value as 1.139. so let's just work out the total value, right? We have worked out this and this is lambda phi. So we have worked out lambda phi and this lambda VV. Okay, this over here, lambda phi, lambda VV. Sorry, lambda phi is this one and this is this one. Okay, now final calculation, lambda E underscore 0.7. we are putting all these values here. From in this equation we are putting these values, right? So K1 we have got it from the table 12. Okay, K1 is 0.7. okay, the two part we have assumed, and connection have this minimum 2 volts. Okay, loaded through single leg. All these parameters K1, then we have K2 0.6 and K3 will be 5. This value we have already got, this 0.09 to 1.139. okay, so if I calculate this, so I am getting value as 1.233. I'll work out the phi value again. So the phi value I'm getting 0.5 1 plus A. That's our equation, and we need to put those values over here. So 0.5 1 plus 0.49 1.233 minus 0.2 plus 1.233, that we have already get, right? So if I work out this, I'm getting value as 1.513. okay, and from here we will work out xi value, phi plus phi square minus lambda E square. I'm writing down in the inverse proportion. Okay, that's why I have put it -1. Don't get confused with that. It's actually 1 divided by this value. Okay, so in between my video got interrupted. Sorry for this. And yes, let's just start again. So this is I am writing down in the -1 format. Okay, so don't get confused with that. It's actually 1 divided by 1.513 under root 1.513 whole square minus 1.233 square. And if I work out this, I'm getting value as 0.418. okay, so from this we get the FCD divided by gamma m0. Xi we have already worked out, 0.418 into 250 into 10 raised to 6 divided by 1.1. so I'm getting the value as 95.06 megapascal. okay, so if we work out the actual compression capacity under flexural torsional buckling, my P will be A into FCD. A is the area, right? I'm not writing the equation again, into 95.06, whatever the FCD value we have got. okay, this is megapascal, so I'm getting value as 380.2 megapascal. Now see, remember, the minimum capacity governs the main your design part, right? So the flexural torsional buckling controls, and if you want to work out the utilization ratio, okay, so whatever the load we have, what was the load we have the load value as 100 kilonewton, right? So if I work out the utilization ratio, your actual load P is 100, right? And design load is PD, what you can say is 380.2. okay, so 100 divided by 380.2, I'm getting value as 0.263. so that is your utilization ratio. Got it? So that's how you can work out these values. Now you can compare these results, whatever the results we have got. See what results we have worked out. So let's just quickly go through that. So first part that we have calculated for the major axis part. Okay, for the major axis, what we have get, see the P value for the major axis we have got as 749.7. okay, so that's the actual compression capacity about major axis. Similarly for the minor axis, in the same manner we have worked out. Okay, that particular value was here itself. Okay, this one is for the major axis. Let me write it down. This is for the major axis, and for the minor axis we have got the value as minor axis. So the minor axis value is 421.8, and we have checked our actual compression capacity for the flexural torsional buckling, right? That we have worked out for the single loaded leg, that we got as 380.2 megapascal. Okay, and utilization ratio based on the minimum value is 0.263. now you can compare this results. Sorry, my camera got interrupted again. So what I was saying, so based on this you can work out and compare these results with your STAAD result as well.